Hello guys, so this is part 2 of the final exam solution for term 182. So what I want to do in this video is basically I want to go over the remaining 16 questions that I didn't solve in the last video. So let's get going. Okay, so for question 15, we're given this circuit and we're asked to find the resistors R1 and R2 respectively. And we have the resistance for this resistor, which is 10 ohms. So the only given in the problem is the power. So we know that the power dissipated through the resistor 1 is 20 watts. So our goal is to use this information to figure out the resistance in R1 and R2. So first off, we have to understand and we have to know that power through any resistor is equal to the current times the voltage. And we know that the voltage from Ohm's law is equal to, so the voltage is basically equal to this, IR. So we could rewrite this equation to be power is equal to I squared times R. So now that we know that the power that goes through R1 is 20 watts, and we know also the current going through R1 is 2 amperes. So, sorry, we're given two things in the problem. We're giving the power is equal to 20 watts, and we're given that the current through R1 is equal to 2 amperes. Yeah, and we're also given that the battery over here generates 3.5 amperes of current. So we're given three things in the problem: the power dissipated in resistor 1, and the current going through resistor 1, and the current produced by the battery. Okay, so through this equation, we could just solve for R, like divide both sides by I squared. So R will be equal to P over I squared, which is as written here. Power is 20 and current is 2, so 2 squared is 4. 20 over 4 is 5. So the value of R1 is 5 ohms. And this is the first part of the problem. Okay, the second part is figuring out R2, the value of R2. Okay, before we do that, we have to understand that all of these three resistors are connected in parallel with each other, and they are also connected in parallel with the battery. Knowing that, this means that the voltage difference across all the three of the resistors is the same. So if you have the resistors connected in series, then this is not true. The voltage will be different in each resistor. But for any combination of series of resistors connected in parallel, the voltage have to be the same across all of them. Okay, so we can now figure out, so now we know the value of R, and we know we know the value of R, and we know the current going through it. So using Ohm's law, we could figure out the voltage. So R1 is equal to 5, and the current through it is equal to 2. And according to Ohm's law, 5 times 2 is equal to 10. So the voltage going through R1 is 10. And since all of these are connected in parallel, then the voltage across R2 is 10. The voltage across this resistor over here is 10 as well. Okay, so knowing this, we could now figure out the current through this resistor. And that's by simply using Ohm's law. So we know that the current through any resistor is equal to R over V. Actually, yeah, sorry, it's V over R. V over R. So if you divide the voltage by the resistance, you get the current. So the voltage across R2, we already figured it out. It's 10. And divided by R, we're already given the value. Sorry, so we're talking about this resistor, not this resistor. We don't know the value for R in this one. So here we know the voltage across it, and we know the value for the resistance. So just divide the voltage by the resistance, and you get the current. And here it happens to be 1. Okay, so the next step is figure out the current through R2. Okay, so if we know that the battery generates 3.5 amperes of current, and we know that some of that goes through this branch of the circuit, and we know that only 1 ampere of the current goes through this branch. So here we're left off with 2.5, and we know that some of this 2.5 will be going here, and some will be going here. And we're already given in the problem that the current through this resistor is 2 amperes. So here it must be 2 amperes. So whatever left off from this will go over here, and that is 0.5. So now we know that this current is basically 0.5 amperes, and that's exactly what I did over here. So I2 is basically 3.5 minus 1 and minus 2, and we're left off with 0.5. So now we know that the current flowing through this resistor is 0.5, and we know that the voltage across it is 10. We could easily solve for R through Ohm's law. So through Ohm's law, R is equal to voltage over the current, which is 10 over 0.5, which is equal to 20 ohms. And that would be your answer. All right, guys, for question number 16. So we're given this circuit, and it's a capacitor charging circuit, which means that once we turn the switch on or connect the switch to this wire, the battery will start charging the capacitor. So we're given, in the problem, we're given tau, or the time constant, or the resistance, or RC. We're also given the capacitance of the capacitor, which we need to convert from microfarad to farad by multiplying by 10 to the negative 6. We're also given the initial current. So what does this mean? So the initial current means that the moment we connect or turn the switch on, at this very beginning, the current through the resistor is going to be this value over here. So this is what we mean by initial current. Because the current is going to change as the capacitor begins charging. So the question is asking, what is the voltage difference across this capacitor after 20 times 10 to the negative 3 seconds? Okay, so in order to figure that out, in order to figure out the voltage through the capacitor in this time, we need to do a couple of steps. So first, this is the first step that we're going to do. We're going to figure out the resistance through this resistor. So we know the value of R times C, or tau. We're given in the problem. Tau is equal to 40 times 10 to the negative 3. And we know the capacitance of the capacitor. So all we actually need to do to figure R out, we need to divide both sides by C. And then you plug in your numbers, and you will figure out that R is equal to 800 ohms. So R here is equal to 800 ohms. Okay, so the next step is using the equation, this equation. So this equation calculates the charge in a capacitor charging circuit. So, but we don't want the charge. So this equation is coming out of your equation sheet, and you have to sort of differentiate between this equation and another equation that is used for a discharging circuit. So if the circuit is charging the capacitor, and you want to figure out the charge, use this equation. The charge in terms of the time. Okay, so we know that this is the capacitance of the capacitor, and we know if we divide the charge by the capacitance, you get the voltage. So we're going to divide both sides of this equation by C. So the C here will cancel out, and Q will turn to V. So now this equation gives you the voltage across the capacitor as a function of time. And we're going to use this equation to calculate the voltage across our capacitor in this time. So before we go ahead and use this equation to calculate our voltage, we need the EMF of the battery. The EMF of the battery is basically the initial voltage across the capacitor. So in order to sort of calculate the EMF of the battery, so we need to use R, and we need to use the current through R. So we're given in the problem that the initial current is this value. So if you multiply the initial current by the resistance, you will get the EMF of the battery. And once you do that, you will be able to use this equation to figure out the voltage across the capacitor. So now everything here in this equation is known. We figured this out. This is the EMF. And we know what RC is. RC is given in the problem. And we know what the time here. So the problem says that we need to figure out the voltage in this time. So you just take this time and plug it in here. And then write this equation to your calculator, and you'll be getting 20.5 volts. So write this equation into your calculator, and it will spit out this answer. And that is the answer. All right, guys, for question number 17. So we're given this circuit, and we're asked to find the voltage difference between point A and point B. So this is point A and this is point B, and we want to figure out. So there is some sort of voltage over here, and there's another voltage over here, and we want to figure out what is the voltage difference between point A and point B. Okay, so in order to do that, first we need to figure out the current flowing in this branch and the current flowing in this branch. And in order to figure out the current flowing in these two branches, we're going to have to add all of the resistors and make it only one resistor. So first, if we have two resistors connected in series, then the equivalent resistance is going to be equal to R1 plus R2. This is the way to add resistors when they are connected in series. But if the resistors are connected in, so here is series. But if the resistors, let's label this S. If the resistors are connected in parallel, then the equivalent resistance is going to be equal to 1 over R1 plus 1 over R2 to the power of -1. So here we have two resistors connected in series, so we just simply add them. So 3 plus 3 is equal to 6. And here we have 5 plus 1 is equal to 6. Okay, so this is the simpler form of the circuit, but it's not as simple as we want it to be. So we're going to further simplify the circuit by adding these two together. Okay, so if you want to add two resistors in parallel, use this equation. So what we're going to do is basically our equivalent resistance is going to be equal to 1 over 6 plus 1 over 6 to the power of -1. If you plug this into your calculator, you'll be figuring out that the equivalent resistor is equal, or the equivalent resistance is equal to 3 ohms. So now we know the equivalent resistance and we know the voltage. So we could figure out the current through Ohm's law. So Ohm's law says that the voltage is equal to IR. So I is equal to V over R. And we know that 24 is V over R, which is 3. That is going to be equal to 8. And as is just written here, the current, or I naught is the current flowing in this simple circuit, is going to be equal to 8. But notice that in this version of the circuit, we have two identical resistors, and we have only one voltage. So if the voltage is the same across this resistor and this resistor, and the resistance here and here is the same, then because current is basically V over R, we're going to have the same current here and the same current here. And we know that the sum of all the currents in all branches in the circuit is equal to the current generated by the battery, which means that I naught, or this I naught, is equal to, have to be equal to the current flowing in here, I1 plus I2. And the only way these two can be identical and their sum to be equal to I naught is for them to be equal to I naught over 2 and I naught over 2. So we know that the current flowing in this branch is I naught over 2, and the current flowing in this branch is I naught over 2. And now let's go from here to this circuit. So in this circuit, we have two resistors connected in series. And as a matter of fact, any two resistors or any number of resistors connected in series, they have to have the same current flowing through them. Now, the voltage might drop when you move across one resistor, but the current will stay the same. Which means that even if you add a resistor in here, the current is going to stay I naught over 2 across all of the resistors. So what does this mean? It means that the current flowing here is equal to I naught over 2, and the current flowing here is equal to I naught over 2. This is true for here as well. And we know that I naught over 2 is equal to 4 amperes. So now we're halfway there, we're almost solved the problem. So now we could just use the loop rule. So let's go ahead and make a loop like this. So the battery is generating a voltage of 24 volts. So in order to figure out the current, the voltage at A, we start from here. So at this branch of the circuit, we have 24 volts generated by the battery. Then once we get here, the voltage is going to drop by I over R. So Ohm's law gives you the voltage drop across any resistor. So we know the current flowing through here, which is 4 amperes. And we know that the resistance is 3. So if you multiply the current by the resistance, and you're going to get the voltage drop. So the voltage will drop from 24 to 12, basically. So the voltage over here will be 12. VA is equal to 12. Now, by the same exact logic, the battery will be generating the voltage here to be 24. And once we pass through this resistor, the voltage will drop by IR. So I is basically 4 and R is 5. So 24 minus 5 times 4, which is 20, is going to be equal to 4. So the voltage at B is equal to 4. Okay, so now we just take the difference. So A is 12, B is 4, and their difference will be 8 amperes. And this here is your answer. This is the voltage difference between point A and point B. All right, guys, for question number 18. So the question says that we have some particle, a negatively charged particle, with a given mass, and this particle is within some magnetic field. So, and because we have a charged particle and it's inside a magnetic field, there will be some sort of magnetic force acting on it, as we have studied, like whenever we have a charged particle inside a magnetic field, there will be a magnetic force if the particle is moving with some velocity. And in our case, the particle has a velocity. So, so what formula have we studied that if we have a moving particle inside a magnetic field, then we're going to have a magnetic force. So this formula over here relates magnetic force with the charge and the velocity and the magnetic field. So the question is asking for the magnitude of the charge of the particle. So we have this vector and we have this vector, and we know the force. We already given the force. So the only unknown in this problem is actually Q. So using this equation, you could just solve for Q. And if you divide both sides by this quantity over here, you will have Q to be equal to this. And the fact that the particle is negatively charged is not going to change anything in terms of the magnitude of the charge or the magnitude of the magnetic force. If we put a negative sign here, it will only reverse the direction. So in this question, we're not interested in the direction. All of the choices are given in magnitude. And so two things two givens are not needed in this problem. So we're given that this charge is negative, and we don't really need that to solve the problem. We're also given that the mass of the particle is this value, and this here will not be used in the solution. So they gave you some extra information in order to confuse you, probably. But as I just said, you just solve for Q in this equation, and Q is equal to the magnetic force. The magnetic force is given in the problem over V cross B, the magnitude of V cross B, and that will give you the magnitude of the particle. So how can we calculate? So the bulk of this problem is basically to figure out this value over here, to figure out the magnitude of V cross B. So in order to cross two vectors together, there are a couple of ways to do it, but in this solution I used the matrix method. So if we have V cross B and you want to use the matrix method, then the top row have to be the first term, or V. So the top row is V, and the second or the third row over here is should be B, or the vector B. So you have to put it in that order for you to get the right answer. If you reverse it, if you put B in here and V in here, this here matrix will not obey this equation, and therefore you will not be getting the right answer. So first, the velocity is given to you as a vector multiplied by a constant. If you have this form of writing vectors, then you could just simplify by multiplying this constant by each term in the vector notation. So this times this, and then this gives you the A component. Then this times 4 gives you the J component. And this times our constant, let's call it C. So C times 12 is going to give you the K component. And for the magnetic field, we only have a K component. So we put it here under the K column. And since we don't have any I or J components, we place zeros in their places. So now, how can we expand this matrix? So first, let's figure out the I term. So if you want to figure out the I term, you're going to have to sort of cover this column and multiply this value by this value, and minus this value times this value. So this value times this value is just 0, and this value times this value is this one over here. So that's the I term. Now, if you want to calculate the J term for our resultant vector, you're going to sort of cover this whole thing and multiply this over here and by this, minus the multiplication of this and this. And you know the multiplication of this times this is just 0, so our only value for the J component is this here times this. So negative times negative is positive. And when you do the matrix method, when you have to place a negative sign when you calculate the J component. So this number times this number gives you a positive number, but we have a negative sign over here because according to the definition of the matrix method that you must place a negative sign before the J term. Okay, finally the K term. In order to calculate the K term, you sort of cover this whole column and you multiply this by this and this by this. And this by this is equal to 0, and this by this is equal to 0 as well. So our K term is 0. So now we have a vector. This over here, this whole thing, is a vector. Like if you cross a vector with another vector, the result is going to be a vector as well. So in order to figure out the magnitude of this vector, we use the Pythagorean theorem, which is just says that the magnitude of any vector is the square root of the sum of the squares of its components, which basically means take the square root of the sum of this term squared plus this term squared, and that will give you this number. So now we know the magnitude of V cross B, so we just divide the magnetic force by the magnitude of V cross B, and you will be calculating the charge, and that will be your answer. Alright guys, for question number 19, this question mainly tests you on how can you deal with the cross product and how to get your directions, when you cross vectors, how to get your directions straight. So the question gave us some sort of electron. So we have this here is an electron. And this electron moves with a certain velocity in the positive x direction. So we know the charge of the electron, it's given in the equation sheet. And the question told us the velocity of the electron. And we also know that there is some sort of magnetic field that is passing through the electron, which has the value of 7.5 Tesla. So we know three things. We know the velocity, the magnetic field, and the charge of the electron. And we're asked to find the magnitude and direction of this electric field. So first of all, the question says that the electron is moving in a constant speed, which means there is no net force acting on it. If there is no net force acting on it, then that necessarily means that the electric force must be equal to the magnetic force. So the electric force is basically Q times the electric field, or the charge times the electric field. This force has to be equal to the magnetic force. So for any magnetic force on a particle can be calculated through this equation. So this is the magnetic force. But the angle between the velocity and the magnetic field is 90 degrees. Imagine so it says in the question that the magnetic field is going into the page, which means if you see like this X, it means that you are seeing the back of the arrow. So this symbol over here means that the magnetic field is going in this direction, into the page. So if this direction is into the page, and this here is the positive x direction, then these two vectors are perpendicular, and therefore we could remove the cross product and make it a regular product, because sine of 90 degrees is just 1. So over here we just removed the cross product, and made it into a regular sort of product. So just divide both sides by Q, and you'll be getting that the electric field is basically equal to the velocity times the magnetic field. Just multiply these values together, the velocity and the magnetic field, and you'll be getting that the electric field is equal to 855 volts per meter. This here is the magnitude of the electric field. And this is easy to find. But the bulk of this problem is to be able to figure out the direction of the electric field. So in order to figure out the direction of the electric field, so we know two things. We know the direction of the velocity, and we know the direction of the magnetic field. So the magnetic force is going to be, if the charge is positive, the magnetic force will be the cross product between the velocity and the magnetic force, field. So if you do this, the force will be coming out of the page. Okay, not out of the page, not to confuse you, like imagine that the magnetic field is heading into the page and the velocity is heading in this direction. So the cross product is basically, you place your hand on the velocity, and if the velocity is going in this direction, you place your hand on the velocity, and the magnetic field is going in this direction. So you cross the velocity to the magnetic field, and your thumb will be pointing in the direction of the magnetic force. So if you do cross the velocity with the magnetic field, so imagine that this sort of arrow is piercing through the page, through the whole page, not only this point. So this is the velocity, and you cross the magnetic field, so the magnetic force is pointing upward. But our charge here is negative. If the charge is negative, then you must reverse the magnetic force to be downward. So if you have this particle, this is the electron, and the magnetic force is acting downward, then in order to counterbalance this force, we want an electric force acting in the upward direction. And the only way we could have such a force acting, such an electric force acting in the upward direction, given that the charge is negative, is to have an electric field pointing in the negative j direction, because we already know that the electric force is equal to Q times E, or the electric field. And if the charge is positive, then the electric force is going to have the same direction as the electric field. But in our case, the charge is negative, so the electric force will have the opposite direction of the electric field. So the electric field has to be pointing in this direction for it to produce a force in the upward direction, and therefore to balance the magnetic force. So your answer is the electric field is pointing in the negative j direction. This is the magnitude and this is the direction, and that would be your answer. Alright guys, for question number 20, we're given this sort of current carrying wire, and the current is flowing in this direction, and the wire is placed in a region where there is a magnetic field pointing out of the page. So when you see these dots, it means that the direction of the magnetic field is pointing out of the page. But if you see this sort of notation, like the X notation, it means the vector is pointing into the page. Okay, so we're given this wire, and we're given that there is a magnetic field and there is a current flowing through the wire, and we're asked to find the net force. So what is the net force? The magnitude of the net force acting on the whole wire, or on the wire that is inside the magnetic field. So if we have a current carrying wire and we want to figure out the magnetic force on that wire, we use this equation. So this equation is coming straight out of your formula sheet, and this cross product can reduce this to a normal multiplication, because the angle between the magnetic field and the wire, the angle between them is 90 degrees. So if the angle between two vectors is 90 degrees, then their cross product is simply equal to their normal multiplication. So now we have a formula to calculate the magnetic force. Okay, so we're given the current, we're given the magnetic field. So the current is equal to 4.5, and the magnetic field is also given in the question, and the magnetic field is equal to 0.24. This is given in that question. Okay, so now the tricky part of this question is to realize that the length of this wire, the horizontal wire, is basically 60 centimeters. So here, the first wire, we know the current and we know the magnetic field, but the length of this wire is just this part plus this part, and this whole part is 60 centimeters. So if you cross, if you multiply every term here, you're going to get this value over here, and this is the magnetic force acting on the horizontal wire. So we have to understand that the direction of the length is the same as the direction of the current. So since the current is flowing in this direction, if you want to cross cross B, so you will assume that the length is pointing towards the same direction as the current's flow. So for example, if you want to cross this length L with a magnetic field which is coming out to the page, you just simply do this, and the magnetic force will be heading in this direction. Similarly, for this perpendicular wire, if you want to cross it with the magnetic field, the magnetic field is coming out of the page, and the wire is going upward in the positive j direction. So if you want to cross this magnetic field with the magnetic, if you want to cross this wire with the magnetic field, the magnetic force would be heading in the positive x direction. So we have two forces, like we have this force acting in the negative j and this force acting in positive I. And in order to find the magnitude of these two forces, we just use the Pythagorean theorem. We calculate the force acting on this wire by the same way we calculated the force acting on the horizontal wire, which is just the current times the length of the wire, which is at 30 centimeters, or 0.3 meters, times the magnetic field, and that will be equal to this value over here. Use the Pythagorean theorem, and you will be getting this answer. And that is the answer for the question, which was asking for the net force acting on the wire. Alright guys, for question number 21, we have this figure, and it's basically some sort of current carrying wire. So we have some current going in this direction, which is equal to 5 amperes. And we're given the dimensions of this square. And we're asked, we were also given the magnitude of the magnetic field, which is pointing towards the positive x direction, which is the green arrows. And we're told, we're asked to calculate the torque produced by the magnetic field on this wire around this axis. So we know that when we have a current carrying wire and we place that current carrying wire in a magnetic field, there is some sort of torque that is going to happen to that wire. And in order to calculate that torque, we first need to assign some sort of magnetic dipole moment for the ring or for this wire. So, and the magnetic dipole moment is basically equal to the number of turns that we have in this ring times the current flowing in that ring times the area of that coil. So it's not a ring, so the technical name is coil. So number of turns of the coil times the current flowing in it times the area of the coil. So once we get that, we could calculate the torque, and the torque will be the cross product between the magnetic dipole moment and the magnetic field. So let's go ahead and first calculate the magnetic dipole moment, which is equal to the number of turns is 1. We have only a single turn in this coil. So another coil with multiple turns would be something like this. So each turn here like constitutes a number on here on the end. Okay, so number of turns in this coil is only 1. The current flowing through it is 5 amperes, which is given in the problem. And the area, we have a rectangle, so we multiply the length by the width. And don't forget to convert to SI units, so meters, 0.35 meters and 0.20 meters. If you multiply each term, all of the terms over here, you'll be getting that the magnetic dipole moment is equal to 0.35. Okay, once we have that, we could now do the cross product. And since we know that the magnetic dipole moment is perpendicular to the magnetic field, so one way you could know the direction of the magnetic dipole moment is by placing your fingers, these 4 fingers, aligning them with the current, and then rotate your hand, your right hand, with the direction of the current. Like so if you align your fingers, these 4 fingers, with the current, and then rotate your hand, the direction will be like this into the board. So the direction of the magnetic dipole moment can be figured out with the right hand rule, and in this case it's into the page. So we know that if the magnetic dipole moment is pointing, imagine that this is this direction is into the page, and the magnetic field is pointing in the positive x direction, then the angle would be 90 degrees between them. So this over here is a top view. Like if you're looking at this setup from above, you'll be seeing that the magnetic dipole moment is heading in that direction and the magnetic field is heading in this direction. So because of the angle between them is 90 degrees, the cross product could be reduced. So basically any cross product is the magnitude of the first vector times the magnitude of the second vector times sine of the angle between them. And sine of 90 degrees is just 1. So This is 1, this cancels. So we're only left off with the magnitude of the magnetic field times the magnitude of the magnetic dipole moment. So we know that we just calculated the magnetic dipole moment, and the magnetic field is given in the question, which is 1.2. If you multiply these two values together, you'll be getting that the magnetic, or the torque, is equal to 0.42 newtons time meters. And all right, guys, for question number 22, we're given this sort of wire that is bent into a circle over here and is straight over here and here. And we're told that there is a current flowing in the wire in that direction. It goes like this, and then it goes like that. And we're asked to find the net magnetic field at this point. So whenever we have a wire, and whenever we have current flowing inside that wire, a magnetic field will be produced. So in order to calculate that magnetic field, each geometric shape has a unique formula. Like when you have a straight wire, you use this formula to calculate the magnetic field. But when you have a circle, when the circle is full, we use this formula. So R here is the distance between the wire and the center of the circle for this one. And here R is the distance between the wire and the point we're calculating the magnetic field at. Okay, so in this question, we're going to use these two equations because we have a straight wire and we have a full circle. But there is another equation that you should not be confused about. And this equation, you can use it when you have an arc, like a non-complete circle, and you want to calculate the magnetic field at the center of the arc. Then you use this equation. But this over here is not something we're interested in this question. So first of all, let's see if the magnetic field produced by the wire is actually going to add to the magnetic field produced by the circle, or are they going to be in opposite directions? So if you want to know the direction of a magnetic field produced by a current carrying wire, then all you need to do is basically place your thumb in the direction of the current, and then move your hands, you move your forefingers. If you move it like this, then the direction of your forefingers will be at the same direction of the magnetic field. So the magnetic field produced by the wire would be pointing in this direction into the page. Because if you do this, your forefingers will be pointing into the page. Now do the same thing to the circle, and if you go ahead and place your thumb in the direction of the current, you will see, and rotate your forefingers, you'll see that your forefingers are also piercing through the board. So with that being said, using the right hand rule, we know that the magnetic field produced by the wire and the magnetic field produced by the circle will actually be in the same direction, and therefore we can add them. So we will have this formula plus this formula, and that would give you the net magnetic field. So if you take mu naught times I over 2r as a common factor, take it out of the formula, then you're going to have this expression over here. If you multiply this expression by 1, you will get this formula for the full circle. And if you multiply this term by 1 over pi, you'll be getting the formula for the wire. And we have a plus sign here because the two magnetic fields are pointing in the same direction. So once you get to this stage, we could just solve for R. So we know the net magnetic field. It's given in the question, but the question is asking about the value of R, okay? So with some sort of simple algebraic manipulation, you could solve for R. And once you isolate R in one side and everything else in the other side, all you actually need to do right now is to just substitute B by this value. And mu naught is just a constant given in your equation sheet. And the current flowing through our wires is just 1.22, which is given in the problem. And if you go ahead and plug these numbers into your calculator, you'll be getting that the R is basically this length. And that is your answer. All right, guys, for question number 23, we're given this sort of setup. And so we have here a wire. Let's call this wire 1. Okay, wait, wire 1 over here. And this here is wire 2. And there is some batteries on both, connected to both wires. And we have some resistors as well. So these batteries will start pushing charges, and current will start flowing at this wire. The same thing is going to happen over here. But battery is going to push charge, and current will start flowing in this wire as well. So when we have two current carrying wire and they are in proximity to each other, some force will be generated between the two wires. And in order to calculate such a force, we use this equation. So this equation is used to calculate the force between two current carrying wires. And the force over here is given in the question, and it's 5.4 times 10 to the negative 5. But we're asked in the question to find the value of R1 in order for this force to be generated. So we're given the R2, and we're given the voltage on both circuits, and we're given the length of the wire, and we're given the separation between the two wires. So using Ohm's law, we could write R in terms of I and V. And we could also write I in terms of V and R. So we're going to use this equation, and we're going to plug I1 in this equation to be V over R. So the force between the two wires is equal to mu naught times the length of the wire times the current in this wire, which is wire 2, times the current in the first wire, which is just V over R, or 9 over R1, over 2 pi D. D is the distance between, or the separation between the two wires. So if you notice, the only non-given in this equation is R1. We know what the current in here. We could just figure it out by Ohm's law, which says V is equal to IR, and I is equal to V over R. And we know V, and we know R. So it just, so the current over here is basically 4.5. So we know the current, we know the length. The length of the wire is just 10 centimeters, or 10 times 10 to the negative 2 meters. This is just a constant. You could take it out of your equation sheet. 2 pi is just a constant, and D is the separation between the two wires, which is 5 millimeters. And you need to convert it to meters by multiplying it by 10 to the negative 3. So now we need to isolate R. We need to put R in one side and everything else in the other side in order to sort of evaluate R. So if you multiply both sides by 2 pi D and divide both sides by this here, you will have this expression is equal to 9 over R. If you cross multiply and then divide by the coefficient of R, you'll be getting this expression. And once you get here, you just plug in your values and you'll be figuring out that R is just 3 ohms. And that is your answer. Alright guys, question number 24 is basically a direct application of what's called Ampere's law. So we have a law that's called Ampere's law. The law says that the line integral of B dot ds is equal to mu naught times the enclosed current. So these two values are the same. If you multiply mu naught times the enclosed current, you're going to get the value of the line integral of B dot ds. So mu naught is a constant. It's 4 pi times 10 to the negative 7. If I wasn't mistaken, it's on your formula sheet. So here, in the question, in the figure, so we have a figure in the exam question, and this figure is exactly as I drew it here. And we have some sort of Amperian loop, and we're given one of the currents is 1.22 amperes, and is pointing into the page. The other current is I2 is 5.31, and is pointing out to the page. So the question is asking us about the magnitude and direction of the third current. Okay, so this Amperian loop these arrows basically are pointing in the direction of integration. So we'll be integrating starting from this point, going here, here, then this one, and then we get this to this one. So we can arbitrarily choose the direction of integration, but in this question, it explicitly says that the direction of integration is counterclockwise. So in order to know the sign of the current, either positive or negative, you need to place your forefingers in the direction of integration, and then your thumb would be pointing in the positive current directions. For example, this current is going into the page, so if you point your forefingers with the direction of integration, then your thumb is pointing into the page as well, so this one is positive. Now, this one over here is pointing out of the page. So your forefinger must be placed in the same direction of integration, and your thumb is pointing into the board, and this current is pointing out of the board, so it has an opposite direction of your thumb, and therefore it's negative. Okay, now we can substitute into this equation. So mu naught is equal to the sum of the currents. We already said that this current is positive, so we have a positive sign over here. This current is negative, and this here, we don't know what's the sign of it until now. So, and we know that the value of this integral is basically given in the problem, and it's this value. So we could replace this here by this. So this now is replaced by this. So the only unknown over here is now I3. So just solve for I3, and you'll be getting that I3 is equal to positive 4.69. And if it's positive, then it should be in the same direction as your thumb. If you place your forefingers with the direction of integration, your thumb will be pointing this way. So the positive current should be also pointing in the same direction as your thumb, which is into the page, as I just wrote over here. And that is your answer. Okay, guys, for question number 25, we're given some sort of cylindrical wire, and the question divides the wire into two segments. A small wire with radius r is equal to 1 centimeter, and the whole wire, the radius of the whole wire is equal to 2 centimeters. And the question gave us the magnetic field due to the small wire only, and we're asked to find the current flowing through the whole wire, or the total current. So we have to understand that there is a formula that gives you the magnetic field inside a wire. So if you have a cylindrical wire and you want to find the magnetic field at any point inside the wire, use this formula. So it gives you the magnetic field r distance from the center of the wire. So it gives you the magnetic field over here. So we're going to use this formula because we know this here is B inside. We know B inside is given in the question, and it's 9 times 10 to the negative 4. And so this here is B inside. So the formula says that B inside is equal to mu naught times the total current in the whole wire, times the internal distance between the center and the point we're finding the magnetic field at, over 2 times the radius of the whole wire squared. So R capital is the radius of the whole wire. So we have all of these values. We have the small r, we have big R, and we have the magnetic field inside. So this is given, this is a constant. This is given in the problem, this is given in the problem. So we can solve for the total current. Through some algebraic manipulation, you could rewrite this equation in terms of I, and then you just plug your numbers in, and you will be getting that the total current is 180 amperes, and that is your answer. Alright guys, for question number 26, we have a solenoid, and there is a magnetic field inside the solenoid. And if you remember from the book or from the presentation you had in lecture, that the magnetic field inside the solenoid will be uniform and would be of this form, like straight lines, straight horizontal lines. And the question says that we have some electrons with some velocity moving in a circle inside the solenoid. So the velocity is perpendicular to the magnetic field. So the magnetic field is heading in the positive x direction, and the velocity is circular, and it's always perpendicular to the magnetic field, like that. So, and we're asked to find this velocity, knowing that the charge is an electron. And we know the radius of the circle. The radius is given to us. And we know the number of turns of the solenoid. So we have 150 turns per centimeters, but we need to convert that into turns per meter. So you multiply 150 by 100. We also know the current flowing inside the solenoid. And we know the charge and the mass of the electron, and that's all we know. And we're asked to find the velocity. The uniform circular motion velocity. Okay, so in order to do that, first we have to understand that there is an equation that gives you the magnetic field inside the solenoid. So if you want to calculate the magnetic field inside the solenoid, you just multiply the number of turns by the current times mu naught. So just plug values in and you'll be getting that the magnetic field is equal to 2.82 times 10 to the negative 3. So once we figure that out, we could go ahead and solve for the velocity. Now, we know that if we place a moving charge in a magnetic field, some magnetic force is going to appear, and that is going to be equal to Q times V cross B. But we know that the velocity here is perpendicular to the magnetic field, so we drop the cross products, and so we have V times Q times Z times B is equal to the magnetic force. So this here is the magnetic force. The magnetic force is causing some sort of centripetal force or causing some sort of uniform circular motion. So, and we know that the centripetal acceleration is given by V squared over R. And if you multiply the acceleration by the mass, you get the force, which is the magnetic force. So this is the mass of the electron, and here is the radial acceleration. Then just solve for V, and you will get this expression over here. The charge of the electron times the radius of the circle over the mass of the electron times the magnetic field will give you the velocity. And all of these values, we have them, either in the givens or we solve for the magnetic field. Just plug these values into your calculator and you'll be getting that the velocity of the electron is basically this value. And that would be your answer. All right, guys, for question number 27, so we have a rectangular region with some sort of magnetic field piercing through it, piercing into the page. And on the outside, we have some circular region. And we're asked to find the magnitude of the magnetic flux flowing through the circular region. So first of all, we have to understand that the magnetic flux flowing through the rectangle is exactly the same as the magnetic flux flowing through the circle. Because the only region where there is magnetic flux is inside this rectangle. So by finding the magnetic flux inside or flowing through the rectangle, we also, by doing that, we also find the magnetic flux through the circle. So we have an equation coming straight out of your equation sheet. It says that the magnetic flux is equal to the integral of B dot dA. Since B is uniform here, so we could take it out of the integral. So it says in the question that the magnetic field is uniform. So it does not change. It's the same everywhere. So it's like a constant. We take it out of the integral. Then the integral reduces to this, the integral of dA. So the dA is basically small areas, and if you integrate these small areas, you basically sum all of the areas inside the rectangle, and you will end up having the rectangle area. So here is the rectangular area. So the rectangular area is basically the length times the width, which is A times B. So A is basically A times B, and that's multiplied by B, gives you the value of the integral, and the value of the integral is equal to the magnetic flux through the rectangle, and the magnetic flux through the rectangle is the same thing as the magnetic flux through the circle, and that is your answer. Okay guys, for question number 28, we're given this square, and we're given the dimension of the square, and we're told that the resistance in this material of the square is basically 0.2 ohms, and we're given that there is a magnetic field going into the square, and this magnetic field is increasing at a rate of 4.96 Tesla per second. So the derivative of the magnetic flux with respect to time is equal to this value. Okay, so and we're asked to solve for the current in the wire, and for the magnitude and the direction of the current. Okay, so in order to solve for the current, we first need to solve for the voltage, or the EMF. And then once we get the EMF, we divide it by the resistance to get the current. And then we use Lenz's law in order to figure out the direction of the current. Okay, let's start by saying that the magnetic flux is equal to the magnetic field times the area if the magnetic field is perpendicular to the area, and if the magnetic field is uniform. And in our case, it does explicitly say that the magnetic field is uniform throughout the whole square. It says that in the question, but the magnetic field is increasing, like it's getting stronger, but it's increasing uniformly throughout the whole square. So we could use this formula. So let's take the magnetic flux and replace it by B times A in this formula. So this here is another formula. It says the induced EMF is equal to the derivative of the magnetic flux with respect to time. Okay, so we just take this over here, the magnetic flux, and replace it by B times A. And that's what I just did over here. So we know that the area of the square is not changing, so we could take it out of the derivative. So we have A times the derivative of the magnetic field with respect to time. And we're told in the question that the magnetic field is increasing at a rate of 4.96. So we just plug your values in. Here is the area of the square, area in meters. And here is the derivative of the magnetic field with respect to time. If you multiply these values together, you're going to get the EMF, or the voltage, induced in the square, and that is going to be 0.03 volts. Okay, once we have that, we could just divide it by the resistance, which is given in the problem, in order to get the current. So we used Ohm's law to get the current. So this is the magnitude of the current. Now we need to use Lenz's law to figure out the direction of the current. So Lenz says that if we have some sort of changing magnetic flux, and there will be some current induced in the wire in such a way to resist that change. For example, if we have the magnetic field to be increasing into the page, so we need to induce a current that produces a magnetic field in the opposite direction to the magnetic field that is increasing. So we're trying to sort of resist the change in magnetic field. And in order to figure out the direction of such a current, we use the right-hand rule. So always let your thumb in the direction of the current. So let's assume that the current is going counterclockwise. So it's going in this direction. And by the way, this is the correct answer. So we're assuming that the current is going counterclockwise. So we place the thumb in the direction of the current, and we rotate the forefingers. So it turns out that the forefingers are pointing out of the page, which is the opposite direction of the magnetic field. So which means that if the current is flowing this direction, it will produce a magnetic field in that direction, or in this direction out of the page. And that produced magnetic field will counter the increase in magnetic field. And according to Lenz's law, this is the direction of the current. And that is your answer. The direction of the current is counterclockwise, because it needs to induce a magnetic field that resists the increasing magnetic field. And that's it. Okay, guys, for question number 29, we're told that there is some sort of uniform magnetic field, and we have some sort of coil, square coil. And imagine that this is the coil, and this here is the area vector. The area vector is always normal to the area we're interested in. So it says in the question that the normal is 30 degrees away from the magnetic field. So basically what it says is that we have this setup. So this here, I drew it from on my own, like it's not given in the problem. But in order to imagine what's going on in the situation, you could say that there is a magnetic field and there is a coil oriented 30 degrees away from the magnetic field. Okay, so this is the first part of the givens. Then we're told that the magnetic field increases from 0.2 Tesla to 0.6 Tesla in 0.4 seconds, which means this is the B initial, and this is the B final, and this is the time. So through this information, and we're also told that the magnetic field increases uniformly, which means we have a line, like to describe the magnetic field as a function of time, we have a constant slope or a line. So if you want to find the derivative of B with respect to t, you just take the slope of the line, which is B final minus B initial over 0.4, which is equal to 1. So dB dt is equal to 1. We're also told that once this magnetic field increases, an EMF is induced in the square, which is equal to 80 millivolts. So we convert that to volts by multiplying by 10 to the negative 3. And we're also told that the coil has 25 turns. Okay, through this information, and knowing that the angle is 30 degrees, we're asked to find the area of the coil. So we have a law that says that the induced EMF is equal to the number of turns times the derivative of the magnetic flux with respect to time. So we could expand the magnetic flux to be A times B times cosine theta, because the magnetic flux is basically equal to the integral of the area dot the magnetic field. In fact, the magnetic field dot dA. So we know in this case that the magnetic field is constant or uniform, so we could take it out of the integral, but we still have the dot product, so we have to multiply by cosine 30 degrees. So if you integrate dA, so you could also take this cosine out, and if you integrate dA, you'll be ending up with BA cosine 30 degrees, cosine 30 degrees. So basically, the magnetic flux can be rewritten as BA times cosine 30 degrees. So this here is basically this. And we know that the only changing term with time, with respect to time, is B. So we could take A and cosine theta out of the derivative. So we have this. N times A times cosine theta times the derivative of B with respect to time is equal to the induced EMF. So the induced EMF is known, which is here, and the number of turns is known, which is 25. The angle is known, which is 30. The derivative of B with respect to t is known, which is 1. So the only non-given in this equation is A. So, and A is the value we're looking for. Like, we're looking for the area of the square. So with some algebraic manipulation, we could just solve for A in terms of the EMF and the number of turns and cosine the theta and the derivative of B with respect to t. And once you get to this stage, you just plug your values in and you'll be getting this answer as being the area of the coil or the area of the square. Alright guys, for question number 30, our last question over here, we are given this figure and it's basically some sort of coil within a magnetic field. Okay, so the magnetic field is uniform and it does not change. There is no increase or decrease in the magnetic flux, but the area of the coil is decreasing because this bar over here has a velocity that is moving in this direction, which means that the net magnetic flux is decreasing. And because the net magnetic flux is decreasing, there will be some induced current through this coil in such a way, like initiated in such a way to sort of counter or resist the decrease in the magnetic flux. Okay, so there will be an induced EMF which will cause an induced current, and we want to figure out the current through this resistor if the resistor has a value of 50 ohms. So in order to figure out the current through the resistor, we first need to figure out the induced EMF due to the decrease in magnetic flux. So there is a formula in the equation sheet specifically designed for, or specifically derived for these sorts of questions. When you have a coil with decreasing area, actually a rectangular coil with decreasing area, you can use this equation. The equation says that the induced EMF in a rectangular coil with decreasing or increasing area is equal to the magnetic field times the length of the rectangle times the velocity by which the length changes, or the velocity by which the width changes. And if you multiply all of these values together, like, you will be getting the EMF. So the magnetic field is 0.8 times the velocity, which is 20, times the length, which is 1/2. And that is going to be equal to 8 volts. And once we have the induced EMF, we could use Ohm's law, which is the EMF is equal to I times R. And if you want to figure I out, you're going to have to divide the voltage by the resistance, which is basically, so the voltage we calculated to be 8, the resistance is 50. If you divide 8 by 50, you'll be getting 0.16 amperes. And this here is your answer. Okay, so this is it. These are all the questions in the final exam. And once more, I would like to congratulate everyone for completing the course, such a fundamental course in engineering. And that's it for this video and for the final exam. So I plan on explaining the rest of the chapters in Physics 102. So I explained some of them in the past, but in the near future, I will explain the rest of the lessons or the chapters we have in the course, Physics 102. So that's it. I'll see you in another video.